Yeah. So firstly, I would like to tell some things about HyDesign tool. So HyDesign tool is being developed at DTU, and it's an open source tool, Python-based open source tool. And whatever Kaushik has explained about hybrid power plants, so we try to model those hybrid power plants in HyDesign. And the main intention is to perform the sizing optimization of those plants, and or either if we have some specific or existing plant available details available, or if we want to just evaluate a given specific design, then we can do it through the HyDesign. So, and it is formulated using OpenMDAO platform, in which we have different components for different technologies, and we try to make them couple together. And then the objective functions that we basically focus upon in HyDesign is the maximization of NPV over capex, or minimizing the levelized cost of electricity. So the sizing optimization basically here involves wind turbine siting and its layout optimization to find out how a big what should be the rated power of the wind turbine, or the hub height, the diameter of the wind turbine and its layout. Then another component we have is for the PV, for the solar plants, like that is the PV array sightings. What should be its different angles of inclination, or what should be the rated power of those PV modules. And another one is the electrical infrastructure optimization. And then the next one we have here currently is EMS optimization. So in EMS, basically we are performing the energy management system operations of all technologies which are there in our plant. So we can have wind, solar, battery, hydrogen, and a grid connection, or either all of them or just a combination of some of them. And this is the like this is the picture which shows how this HyDesign documentation look like. And if you can also parallelly open the file that Matthew has shared with you, from those files you can easily follow these links, and you can open parallelly in your laptops, and we'll go through them after few slides. And then just giving an overview of this HyDesign tool, how it works like. So we have, it will start with the figure at the top. So it's a smaller version of HyDesign tool. So we have the weather data module, where we extract the weather data for the given location where we want to have our hybrid power plant. And from the weather data, we'll get wind speed and solar irradiances. From there, we have our wind plant modules and PV plant components or modules, you can say, which processes that data for a given specific design variables of wind turbines and PV arrays. And we get the respective wind and solar power profiles from those components over for 1 year or so. And then we use that data to fed into the EMS, and where we perform the energy management system operations, considering batteries or battery with the degradations and everything. And we try to find out how we should schedule, how we should perform the operation of our hybrid power plant over its whole lifetime. And once we have the operational time series, then we'll go to the finance component, and then we try to do some calculations based upon like calculating the capex, opex, and other economic metrics like NPV, LCOE, IRR, and all those things. And then when we have those metrics, then we have our design variable, which is an maximization of suppose NPV over capex. So these are the internal loops, and then from in the outer loop, we again perform the HPP sizing optimization, and we try to find out what should be the better size of our plant. And then again, we fed those design variables back to the weather component to get updated wind power profile and solar power profiles. So this is how this process goes on, and we try to find out what should be the best optimal size of my wind plant, or PV plant, or battery size, and other things like if it is P2X, then electrolyzer size, so that we can maximize our investment, our profits over the lifetime operation of the plant, or it can be like minimization of levelized cost of electricity. And the diagram, the bigger diagram is basically more detailed one of the smaller one, where you can see the different connections between all these components, inputs and outputs. So why it is a coupled optimization? Because the outputs of one of the component is being used as an input of the another component. So that's how they are closely linked. And open MDAO platform gives us the flexibility to fetch the inputs and outputs and very easily connect them with another components. And it is not required that all of those components should be of kind of similar structures. So you can have wind power plant module in a totally different atmosphere. You can import that model from somewhere, and you can have EMS of any other formulations, and but still you can easily connect them. So now coming to the methodology, what we use for doing the optimal sizing of hybrid power plants are basically we use only three types of input data. One is the electricity prices. Why I have mentioned here spot market and balancing market, because our exercises today are more focused upon these two market structure. So we need the electricity prices, and then we need the site location, latitude and longitude, because we need to extract the weather data. And then we need to know the technology's cost, like what is the capex and opex for wind turbine, for solar PV panels, for grid connection, balance of system cost, balance of plant cost, and all those associated costs with a hybrid power plant. And then once we have these inputs, we perform the whole sizing optimization that we just saw in the previous slide. And as an output, we get some values for the design variables, which are related to wind, solar, and battery. And the output of this optimization problem is basically the financial model parameters, which are NP over capex, IRR, LCOE, annual energy production, and number of batteries we have used over the whole lifetime of the plant. So yes, if there is any question up to this point, then we can take that up before proceeding into the more towards the exercises part.
Actually, I just have one question about HyDesign. You said you have whether these inside HyDesign, do you also have price signal and models for technology cost evolution and things like this included in HyDesign, or is it something we have to elsewhere?
So no, technology costs that you have to find on your own for any respective year that you want to start with. The weather data module is there, but currently for the sake of exercises, we have provided some example sites data already in the HyDesign, so that can be used directly. And the price signal, that is what we need to provide. And that price signals we get from Balmoral balancing toolchain that Kaushik has explained in the previous session. So those two things we have to provide, but weather data can be extracted using the HyDesign itself, or we can use the example sites data already available. But for getting that weather data, we need to access Chorus, and Chorus is again a tool which DTU has developed, and it's not an open source. So if you are in the DTU network, you can use that through HyDesign, but otherwise you need to ask us, and we'll provide you that weather data. Okay, so as we have not many questions, so let me continue. So yes, now just to give you an overview of the financial calculations that we do, there are few equations which represents how the total capex, total opex, or revenues, and net present value, which is NPV or internal rate of return, and all these things are calculated. So this slide can be helpful for most of you while you were performing exercises. So if you get any questions or queries regarding the values and how they are improving or deteriorating in different case studies, can always refer back to these this slide to see how these values are calculated. And then I have just presented some results from one of our paper mentioned here in the reference. So here, This is from one of the paper which is recently published on HyDesign tool. So here we have performed some case studies on 3 example sites in India, which are like good solar, good wind, and then bad solar and bad wind. So we have 3 sites, we analyze those things. So one analysis was made with the objective of minimizing the LCOE, and the another scenario was maximization of NPV over capex. So when we perform these simulations, and that what we have observed is, if we look at the design summary, so we have this we can see that if it's a good solar site, so our sizing optimization is not preferring to invest in wind plants. So we have mostly solar, and it's kind of opposite in the good wind site, where we have mostly wind and there is very less solar. And uh, another thing is that if we look at the objective function differences, so if we are having the objective function as minimization of levelized cost of electricity, so it will try to minimize our investments as much as possible. So because of that, it is not preferred to invest more in batteries. So you can see in the objective function with LCOE columns, we have batteries as almost zero in all the cases. But when we have the objective function of having maximum NPV over capex, then we do have batteries, because what it will try to do is it will try to minimize the curtailments, and with that it can get more revenues, and that can make up all the investment costs that we have made with expensive batteries. So it is also important that what objective function we are selecting for our sizing optimization. And of course, like if we have a positive NPV and if we have a higher internal rate of return, that indicates that it's a good business case, and we can go ahead with it. But of course, the negative values are not generally preferred. And if you are trying to minimize LCOE, then you may find a negative NPV in some cases. And then now coming, before proceeding ahead to energy management system, I would like to make a note that as we are doing most of the exercises today in Google Colab, and it has a very lower computational power, so we'll not able to perform sizing optimization in on Google Colab. What we can do is we can just do the evaluations of some specific designs, and then some sensitivity analysis can be performed with varying the sizes, and we can see how it is impacting our objective functions. So, but you are most welcome to install HyDesign on your laptops, and that will help you to do the sizing optimizations as well. And I'll show you how we can do all the installation processes later on. So coming to the energy management system model, this is if we are only considering spot market, like that's a day ahead market, then in that case, the objective function is quite very simple, uh, where we are just trying to maximize the revenue, and the revenue is earned by selling the electricity to the grid at the spot market prices. And those prices we are getting from the Balmoral model that Kaushik has explained in the previous session. And then there are just some equations, constraints on the power balance, on the grid capacity, grid connection capacity, and on the battery power and battery energy capacities. And yes, battery storage operations constraints are there. So what we are trying to do here is we are giving some inputs to our EMS, which we have obtained from the other components in HyDesign. So we have wind power plant power time series, solar power time series, electricity price time series, and battery characteristics. And then we are performing the EMS. And then as an output, I'll get to know how much electricity we will be injecting to the grid at different intervals of time, and what will be the curtailed power, and how my battery operation will be there. So throughout the lifetime of the plant. So this is EMS for only spot market. But what has been observed is that if we do a follow-up from the discussion in the previous session, So if we are participating as an hybrid power plant owner only in the spot market, then if we are moving towards the real time, then there we will have a good amount of forecast errors, and it might not be possible like whatever we have forecasted for wind in the day ahead will be same in the hour ahead or near to the real time. So what we have tried to do is we are trying to consider two markets at the same time. So here, considering the computational challenges with the open source tools and platforms, we have just moved towards the hour ahead market. So it's a 1 hour ahead market from the real time that we are referring here is as a balancing market. So we are considering a day ahead market, which is like 24 hours before the real time, and a hour ahead market, which is like 1 hour ahead from the real time. So we are considering wind forecasts for those two time horizons. And then again, we are trying to do our whole evaluations and sizing optimization to identify, like, for example, if I have scheduled my battery completely in day ahead, but I can see in closer to the real time, I can see that there is a sufficient amount of imbalance in the system, and that imbalance is positive, like I have excess of power in my system. So maybe there is a requirement of a down regulation at that particular time, and I want to charge, it's good that I'll charge my battery at that interval, but I cannot make all those decisions just by considering spot market. So I have to also consider what could be the forecast in like in a day hour ahead, so that I can keep my battery little bit reserved so that I can use it in the hour ahead markets when there is a need of up or down regulation because of the imbalances. So this is what we have tried to basically make the operation of battery more efficient, so that being a hybrid power plant owner, we can earn more profit, because of course upregulation prices are much more higher than the spot market prices. So for that, firstly, we'll run the spot market model only. And then after that, once we have the outputs from them, then we go to the balancing market. And there we consider new forecasts on wind power, the up and down regulation prices, and the system imbalances. And these all values we are getting either from Chorus or either from the balancing tool chain that we just saw in the previous session. And from that, I'll now get the corrected uh, or improved values for my uh, different profiles of power that I'll be providing to the electricity at the spot market price, or as an up regulation or as a down regulation, and then accordingly we can have the revenue calculation. So
I have a question.
yes.
The price for the spot market and the balancing market, they are output of the balancing tool, or they are from the NSOE or an organization that publish this kind of.
Yes. So these prices can be from any platform, from NCOE or from anywhere, because it's an input to the HyDesign tool. So it can be from anywhere. But we at DTU, we are using the prices that we are getting from Balmoral and balancing tool chains. So because in those two tools, we get it for all the regions in Europe, so we can use it directly. But if someone has prices from NCOE, or if they have their own forecast for those prices, they can also just add them in the HyDesign and they can use it.
The input is a text file.
It's a CSV file.
So a CSV file. So you just change the CSV file as input and use your own prices.
Yes, you can use that, and I'll be showing during the exercises like how you can change your input values. And that was that the only question? Okay. Okay.
Then I just have one question. You said so you try to model the balancing market through inputs that are the imbalance of the system, and you're considering like whether is a perfect because then you don't have imbalance due to bad weather.
No, here if you look at this, so we have the wind forecasting day ahead, which we assume cannot be perfect. So we are again taking a wind forecast in the hour ahead. So now we assume this wind forecast to be perfect. And then this system imbalance, this is at the plant level, right? Those wind forecast errors. But now at the same time, if I'm connected with a system, then system can also have some imbalance because it will be an aggregation of the whole area. So our up or down regulation services will be dependent upon the system level, not like what as a plant we have. And this is a bit complex mathematics for EMS for balancing market. So that's just like what has been implemented in the EMS. So maybe it is again like maximization of revenues which we earn from the spot market, which we earn from the up balancing market. Like up regulation prices are added to the revenues, while the down, if we are doing the down regulation, that we subtract from the revenue. And then we have a penalties. This is to make sure that at least what I have like promised in hour ahead market, I'll try to not deviate that in the hour ahead schedule. So these are for penalties for meeting up what we have promised in the spot market. And then we have some constraints similarly again on battery charging and discharging and its SOEC and the hybrid power plant outputs. And what we are trying to make sure here is that there is no bidirectional flow from the grid. So whatever we are producing, we can just only sell it to the grid, but it's not like the case that system imbalance is, I can say, positive. That means we have excess of power. So I'm taking power back and I'm charging my battery. So that is not allowed because there are some grid connection rules and codes, which there are some rules coming up. So from that, it is being said that uh, hybrid power plant can be not be like a with the bidirectional flow cannot be preferred. So it should only give, otherwise there could be a lot of energy arbitrage. I can put as much big battery as I can and I'll take all the power from the grid when there is excess. So that is also kind of made sure here. And then, okay, so this was still, this point, there was some background upon HyDesign and EMS. And if everyone is fine, then we can move towards the exercises and we can see how HyDesign looks and how it works. So for this, I would request everyone like to open this slide deck and open the links that have been mentioned in this slide, which maybe I also. Yes. I'll just share my first screen here. So I'll also. So I hope everyone is able to open this particular documentation link to the HyDesign. And then firstly, I would like to take you through a tour to like how HyDesign repository looks like and what just happened there.
It's about remaining time.
I think, anyways, I think everyone can see, right?
Yes.
No, it's okay.
Yeah. Yes.
Okay, that's fine. Even, you know, we can turn it off because I'll be mostly working with screen one. So, yes. So this is the repository, GitLab repository for HyDesign tool. And here we have different files. So if, as Matthew was saying, like someone of you has asked about the question about the electricity prices, so I'll try to show you how to navigate through it. So if we go to this HyDesign folder, here we have different further folders. So if you need to go to the examples, and then maybe we can select Europe. And in Europe, you can see we have these input files. So this is 2030 electricity price file. So you can open, like if I'll open it here, it will take a lot of time to load, but you can use this file, and there will be different regions available for different prices. Maybe I can show you it to you through my laptop. Yes. So yeah, so this is the electricity file prices file where we have different regions in across the Europe. So if you, this is the data which we get from Balmoral, but if you have data from NCOE or any other platform, you can easily modify this particular file, and you can do the evaluations based on that. And similarly, we have another input file here. You can see the same folder in the GitLab also, but I'll try to show you from my laptop because it's easy for me to open. And then you can see this one more input file, which is .yml file, which contains most of the cost related inputs for the hybrid power plants. So here the first input is the G megawatt, which is the grid capacity, which is 300 megawatt right now. And the N life is the the lifetime of the plant, which we are considering to be 25 years. And similarly, we'll have the values for wind turbine cost, civil works cost, and all the reference values. These all values currently are available in HyDesign now, is taken from Danish Energy Catalog, the recent version of it. But you can use any other values that you get from the suitable references as per your requirements. Then we have the cost values for PV, and then we have cost values and other parameters for batteries, for the electrolyzers, if suppose we are having P2X in our hybrid power plant, then a value for WACC and discount rates, and all the other things which are required for financial calculations. So these are some input values which we have, which we are using. So uh, yes, and then as I mentioned earlier, that we have already provided some weather data for specific sites. So we have these, I think, I think 7 or 8 example sites in Europe for Denmark, France, and Germany, with good solar, good wind, and bad solar, bad wind, like that. So these are already uploaded weather data for these sites, so you can use it directly. And then we have here one more file which is called example sites. So in this file, you can see the details of all example sites that we have there in HyDesign, which specifies the latitude, longitude of those sites, and from where we are taking the weather data, from which file we have to specify the file name, from where we are taking the weather data. We have to specify here the file name from where we are taking the technology cost data. And here it is the file name for the electricity price time data. And this is for hydrogen demand. So this is a brief introduction about how different inputs data you can feed it into the HyDesign, and you can go travel across this HyDesign repository. So if you want to know, like install this HyDesign thing on your laptop, then we have installation guide available on the documentation. So you just need to follow these steps, and it's a very simple installations. And the only thing is that you need to have like Anaconda installed in your laptops, because some organizations doesn't allow Anaconda to be installed. So you have to just get that checked. And if there is any question regarding this HyDesign repository or input data, please feel free to ask, then we'll proceed towards the exercises.
So it's everybody online managed to open the
Okay.
file, so it's okay.
That's great. That's great. So if I'll come back to this my presentation, which I have already shared with you. So if we see, then we have I have a plan to do two exercises. So one will be without balancing market. So first one will be the advanced HPP model, in which we will be evaluating a hybrid power plant design just only for spot markets, where we are assuming the wind forecast in the day ahead is perfect. And it's a simple model. You have seen the EMS equations were just like 4 or 5 equations. So we'll try to run this exercise, and we'll try to get a good hands-on on this, how this Google Colab notebook works with this exercise. And once that's finished, then we'll go to the another exercise, which will be the other with the balancing markets. And then I have like given some tasks in these slides that will majorly involve the comparison of the results of these two exercises and doing some sensitivity analysis. So I would request everyone to I think all of you can see this these tabs in the tutorial section in the documentation of HyDesign. So I would ask everyone to open the second tutorial, which is advanced HPP model. And if they do so, then they can see the tab at the top in blue color, that is open in Colab. And just open this one. And if anyone misses out any step when I am explaining something, you can raise your hand. I can be a little bit slow, or otherwise, for your reference, you have a slide deck with you, which explains every step. So you can also follow those slide decks as well. So if you look at this notebook, then what is needed to be done is to run each and every cell one by one, and just make sure that you are not skipping any cell in between. And it will take time. Just do run anyway. And it will take time for the second cell to complete the execution, because it will install HyDesign. And another small tip is that whatever session you will run here will not get saved as such. If you run the another session at the same time, everything you have done in this one will get removed and lost. So try to download and try to save the results as being prescribed here, so that you can finish up your exercises in the, like, I think we just have almost 1 hour left for the exercises. Also, you can open multiple Google Colab notebooks at the same time to make things faster. So, oh, I didn't know. That's quite informative thing that I got to know. Okay. Like, I am opening the second exercise notebook also parallelly, which is HPP with multiple energy markets at the same time, so that. So in the meantime, when it's running for everyone, we can go through the slides once again. So the step one was to open the required exercise file from the documentation, and then the next step is to open that in Colab. And then after that, what I would like you to notice is that once your HyDesign installation is done in Google Colab, then you have to run again all the cells. Then you can see one cell in which the name of the example site is mentioned. So make sure that this example site for today's session is Denmark Good Wind, because we are going to mostly work with the sample site 9. So, but if you want to use HyDesign for any other studies of your own, then you can change the site name here.
You do not have a Reunion Good Solar?
We'll try to add this. Just provide us the coordinates, then we'll add the weather data. And then after that, we have another cell which gives the values of different initial designs. As I mentioned that we are doing the evaluation, so we have to specify some design of our hybrid power plant already. And since currently Chorus is only giving us the forecast errors with the wind power, so the solar power forecasts are not yet fully calibrated. So we'll focus in this session only on a hybrid power plant with wind plus battery plus grid connection. So you can make the solar megawatt here as 0. Like I think it's already there by default in the exercises, but you make sure that your solar megawatt is 0. And then you have to define some size of the wind plant. So wind plant size in megawatt is defined as a product of number of wind turbine and the rated wind turbine power. So for example, P rated is generally 5 megawatt as per the Danish Energy Catalog. It's a reference value, and you can have, suppose, wind turbines, 70 wind turbines or so, then you can have a 350 megawatt of wind plant, 70 into 5. So this is one thing that you have to take care of. And another thing is battery, because so you can have like we have to specify here battery power in megawatt and the battery energy hours, so that we know the energy capacity of the battery in megawatt hours. Some of the values are already provided in those exercises as the default values. It is fine for today, considering the time that you go ahead with those values, because we had made some tests with those values and they are working fine. And if most of you are done with running all the cells in Google Colab up to this point, then I can move further to the outputs. But
just an explanation on the different parameters. Clearance means the distance between the wind turbines.
And the clearance is basically the hub height minus the rotor radius, like the clearance from the ground.
Okay.
The bottom tip of the blade to the ground.
And SP, the second one.
Specific power.
Specific power. So it's the total power installed in the.
No, it's again a reference bar. It's in watt per meter square.
Okay.
Like it is the design some reference parameter available. So okay, got the results. How can we make sure that everyone has done this thing?
So do not hesitate, the people that are online, to say if you have issue, if you are not able to get some results, perhaps you can share your.
Should we set the exact same parameter because on the default one?
No, just keep the values which are there in the default notebook. This is just an example in the exercises. My recommendation would be to keep the same values which are there in the notebooks right now. Don't change them. And considering the limitation of the time, I would suggest if you open 2 notebooks for the 2 exercises at the same time, and just run them, because then we can do some sensitivity analysis quite quickly. Let's wait for, I think, 5 minutes for everyone to finish running both notebooks completely, and then I can move further with the tasks. Is that fine, Matthew?
The last cell of the notebook is just generate a CSV file. There's
Yes.
nothing displayed on the screen. So
Yes, exactly. So you can see, like I can show you, if you click on that, the bottom, the fourth one, the fourth symbol, yes. So you can see here the files which are generated as an output.
it's possible to share this screen with everybody.
I'll explain these steps afterwards.
Oh, okay.
So that's why I said, like, I just want to wait for maybe like 4 more minutes till to so that everyone is done up to that step for both exercises. So maybe we can start again. Yeah.
Managed to be finished.
Yes. Okay, so if I'll go by the slides, then we can see after running the few of the cells, you will see at some stage the outputs like this. where we have the values for all the financial metrics and other things that I discussed with you during explaining that sizing diagram. So we have, I have just put some full forms for those abbreviations. So we have the value for net present value, levelized cost of electricity, total capex, opex, and AEP here defines annual energy production. GUF is grid utilization factor. So it is basically AEP divided by the grid connection capacity, like how much uh, of the total grid capacity we have used throughout the operation of the hybrid power plant. And then total curtailment is something which can be of interest for you during the exercises. And the number of batteries, uh, like how much number of batteries replacement has been done throughout like 25 years of the operation of the plant. So don't go by the numbers given in the slides, because these are some reference values, just a screenshots, but the actual value you will have in the notebooks for the given case. And then now the next thing is how to download the output files and plots. I'm saying this because, as I mentioned, every time you reopen or something, your outputs will get lost. So just make sure to download those values. So for that, what you need to go to is clicking on this symbol. I can show you directly here. So clicking on this symbol, like which calls files in your collab notebook. If you click here, you can see that you have these files, EMS out.csv and output.csv. So you can just click the three dots and download this file and rename it whatever you want to, and just save it just for, I'll say, 1 hour at least. Save it in your laptop so that you can make some comparisons for the tasks that I'll be discussing with you after this. So if we'll just scroll down a little bit, so I have tried to add some Python codes just for you to make sure, like, to understand how you can plot the different parameters. So you can see how we can do the plotting of these results and how we can study how this hybrid power plant is working. So for example, if I'll go with this graph, which I'm just showing on my screen. So we can see that the blue curve is showing the wind power, and the orange one is PV, which is 0, because we have kept it 0. And if we see the green line, most of the time green line is following the blue line, and when wind power was excess, was more than the grid capacity. So at that time, what we are doing is we can have the curtailment. We are having the curtailment here. Once the after that, what will happen is, firstly your battery will get charged, and when your battery is full up to the capacity, then after that the rest of the power will go into curtailments. So that is the idea of doing the sizing optimization, like to identify that optimal size of the battery, so that we can reduce the curtailment. But at the same time, if I'll put bigger battery, it will add to the cost. So we have to find some intermediate value which can we can afford cost for, and there is not much curtailments as well. So you can see at this particular time the battery is maybe full, its SOC is full, that's why it's going into the curtailment. And if you, this is a very simple time window, there is not much, but if you want to see it for more days, so we can end days of plot, we can change this value to something, for example, like 167, and we can see the plots again. So yeah, this becomes more clumsy, but you can see how it's working. And then the results of this whole EMSs are getting saved into the CSV file, the whole operational behavior of the hybrid power plants. And the output variables, which we have just seen, the values of NPV and all the other things, they are saved into output.csv file here. So for this base case, you have these files you can download and just rename it or whatever you want to as per your convenience. Or also you can change the file name here in the notebook itself, so that it will get saved by that name when you execute this cell. And The same thing is there with the another exercise file as well. So both have the completely same structure, and it's just that their implementation is a little bit different. So I hope everyone is good to go with up to this step, so that after this I can just explain what are your tasks that you can do in remaining 40 to 50 minutes, and um, then I can leave up to you. I think everyone is good.
Yeah.
Okay. So yes. So in today's exercise, what we are going to do is, firstly, I think first three steps have already been done. So first we have to run the exercise with only HPP participating in spot market and just save those results. In the next step, I think you have already run the another exercise, which is with the multiple energy markets. You have to just make sure that it will work only with the wind plus battery plant. So make solar megawatt as 0. Now, by default, there are some specific design given for this hybrid power plant. So here we have considered wind as 350 megawatt, grid connection as 300 megawatt, and battery as 100 megawatt for 3 hours. Like that's energy capacity is 300 megawatt hours. So now, what is required as a part of this exercise is that you have to make a comparison how your NPV or NPV over capex or LCOE, how they have improved or changed for exercise 2 in comparison to exercise 1. Like if we are considering balancing markets as well, how we can earn more profits on more revenues. So that is our one idea behind doing this exercise. And the another thing that could be done is you can try changing the size of the battery. Probably you can try to decrease or increase it, and then you can just try to plot some sensitivity of, like, for example, the objective function, which is NPV over capex with the battery size. And then the another thing that can be done is you can change the grid connection capacity. Like it is 300 megawatt right now, you can make it 100 megawatt, and then you can see how much overplanting can be done. And now for these exercises like this, I think 3 points that the last 3 points that we have in this slide. What is required for you is to change the battery size first, which you can easily do in the notebook itself. But the second one, but the last one, which is the grid connection capacity, you cannot change it directly in the notebook because it is given in the .yml file. It's an input parameter. So for that, how you can change the input file data to use in Colab? So as I have shown you through the Git repository, how we can get these files. So here we have hppparts.eml file available, and even the link is mentioned in the slide. So you can just download this file from here and save it in your laptop, and then you can change the grid capacity here. And once you change it, you save this file with whatever name you want. And then the next step is in the cell where we are defining this variable called sim_pars_fn, you just need to put the right name of the file here. So I know it's a bit confusing, but I'll try to show you through the Google Colab what you need to do. So yes, so once you have downloaded the YAML file from the Git repository, and then after that you have made changes in that file and saved it, then after that, in the same files folder which you have on the left hand side, you can click on this upload folder, upload symbol, and then from here you can upload the corresponding file which you have just renamed, and you can see it here in this working repository. And then if you see this fifth cell here, now we are defining it with some predefined file path, but you just need to delete this, and with a single inverted commas you just need to mention the new file name, and that's how you can change the grid capacity, or even you can make battery more expensive, or you can make can change the cost of wind turbines, and you can do whatever kind of sensitivity analysis that you would like to do. So this is this is the kind of exercise, and all the steps are already mentioned in the slides if you miss any one of them. So, and then you can use this particular template given in this slide to put your results. And you can, like, for example, you can change the size of, as I said, battery, or you can change it for wind also. For example, site 9, and check these values for 2 or 3 configurations, and then you can compare it with the exercise 2, and you can fill up this table accordingly.